Let's get started. Okay, so we're going to jump back a couple of slides and then continue. I just want to actually wrap up a couple of things from the end of last lecture that we did rush through a little. If you can't read the small text over here on stage left, don't worry about those are notes from me. You don't need to read those. Anything that you need to read board work wise will be on the right. I don't expect there to be much board work today. In general, where there is board work, well, it's not going to be automatically recorded on Zoom. Speaking of which, we're recording this on Zoom, so if the mic can hear you, you're being recorded. Everyone consents. We're good. Okay, two-party state. Okay, so a quick bit of logistics. So you do have recitation this week. There's not going to be a whole lot in it. Your TA, you're going to get to meet your TA, and he'll be going over the self-assessment quiz, which you're supposed to have done by midnight tonight. So do actually do that. The coverage of what the answers are supposed to be and why is going to be more useful if you've at least attempted it yourself. I will be putting out a poll for when my Wednesday office hours should be so that I can actually make sure that people can make at least some of my office hours. So when that goes up, do try to actually respond. Otherwise, I'm going to put them wherever the people who responded said they could make them. Cahoots will be doing starting next week. And again, let me know if there are any recording quality problems with this, since we did want to have these recorded on Zoom. Multiple people have asked. Okay, to pick up, nope, lost focus. There we go. Okay, so to pick up where we were at the end of the last lecture, more or less. So this is sort of our view of a early modern era machine. It's got a bunch of cores. It's got some L3. It's got some things that aren't cores at all. Right, so it is in fact an SoC. I would actually argue that while everything went multi-core 2005, 2006, the multi-core era only lasted until 2008, and everything after that has been the heterogeneous computing era. But we'll get to more on that later. Okay, well, one thing I did want to note that I didn't talk about last time. If you look at the differences between this die photo and this one, even ignoring that the second one does not have a GPU on it. And sometimes they do, sometimes they don't. If you look at where the area went, a lot less of this 2020 design is core than your 2012, 2013 era has. Well, right? A lot more of it is memory. Right? So what we're using our transistor budget for as a function of time continues to change. Right? So microprocessors were a revolution because you could fit an entire processor pipeline on one chip. From manufacturing integration and all sorts of other practical perspectives, this was enormous. But once you could fit more than one core in a chip, do you just keep filling it with cores? Do you expand your memory system? Your set of possible design options expands radically. All of these things are possible, right? So in particular, if you think back to the slides much earlier when we were going over Dennard scaling, and you look at that Tylera chip, that's a lot of core. Core, not a lot of memory system. Right? It's optimized for very different workloads. There are also some thermal and power concerns that will turn out to be very important here. Cores are toasty. Cache is cold, relatively speaking. Right? It's still warm. Right? You don't necessarily hold all of your SRAM in your hand, but compared to the core, it's very cold. Much lower activity factor. Okay. And that sort of also plays out in these limits here. If I'd wanted to fill the whole thing with nothing but cores, even if that was a good design, which it actually isn't, you want a memory system. Memory systems are important. This is not the TDP that you'd be hitting. Okay. So to just sort of wrap this up, as you go to increasingly resource-rich designs with multiple cores, with a lot of different possibilities, even in what parts of the memory system, how many levels of the memory system you want to put on chip, right? Your design space expands, and depending on what it is you want to do, you will make different decisions, right? Even in terms of placement on the chip, right? You put a memory controller in the chip, great, this is good. But that memory controller is not equidistant from all of the multiple cores on your chip. Right? They're entirely new optimization concerns at both the hardware and software level in managing these resources as you put more and more things on chip. And finally, and this is the number one biggest change in sort of the mental model of growth from the sort of pre-2005 period, is none of this is going to be free, or at least very little of it is going to be free to all of the other higher layers of the stack, right? If I give you twice as many cores and you have a single threaded program, your benefit is possibly nothing, possibly negative, right? Hardware was giving you instruction level parallelism for free, this transparent improvement for basically 1980s, 90s, good 20, 25, 30 years, right? Where the contract was very simple. Buy new hardware, everything you're doing before just gets better. No changes required on your part, right? By 2005, well, the deal was changed, right? And by not too many years after, even the deal that they claimed they were making was changed a little bit again, right? So until you can actually leverage all of these resources together, right, having more resources doesn't do you any good. So do keep that in mind, again, when you think about optimizations, right? What workload are you optimizing, or what workloads, multiple, right? What is the nature of what you want to optimize for? So we will be covering a lot of this over the rest of the course of the class. But now for some review. Okay, so we finished the overview. And now let's go back to stuff that's going to be mostly review. So when you start thinking about what it is that you are going to optimize for, you have to pick some metrics. Okay, and obviously, if you are a data center, manager, or full-on hyperscaler, your purchasing perspective is pretty important, right? If you are Google, there are a whole bunch of economic concerns that come up in your interaction that you can actually leverage with Intel and AMD and so forth. Actually, here's a little fun fact. AMD has contracts with Google to do all of their verification work. Amusingly, the companies no longer have the resources to run all of the verification experiments without using cloud scale services. And so there's actually some interesting feedback loops that wouldn't have existed 10, 20 years ago. Yes? No, but I mean, here is a design we're working on that we haven't built yet. Before we go build it, we want to help understand that it actually meets specification. Yeah. So there's a very different set of relationship leverage dynamics than there used to be, right? Because with hyperscalers, they create their own market demand, right? If Google doesn't want your chip, that's kind of bad, right? And you go back 20 years and some company doesn't want your chip, you're like, fine. And, right? But now you're losing out on enormous classes of market. So they listen a little more intently these days to some of the companies that are actually involved in making sure that things work. And so there's some back and forth there, because again, Google's idea of whether something works is very specific to Google's workloads, right? Which you're not going to get access to unless you're claiming that you're going to listen to them and make sure it works for them, right? So how you actually even come up with what you actually want to measure is there's some politicking and money involved there as well. So I'll end that digression there. Okay, but it's going to be a recurring theme. Is, as I mentioned, there are lots and lots of design options. So you're going to pick whatever your actual points of comparison are. You're going to pick your metrics. And your goal is going to be to actually try to understand, and this is, again, increasingly complicated in a complicated system, where the right places to make changes are if they're not met, right? So if I have a simple 5-stage pipeline, like we had in 331, and I look at where all of my performance bottlenecks are, I can probably nail down exactly which components are responsible for a lot of my stalling. If I have a 16 cores, 2 threads each, running a complicated networked workload, and it's a little slow, out of my 20 billion transistors, why was it slow? That becomes an increasingly harder question to answer, right? So Picking your right metrics, picking the right non-aggregate data to collect will help you even understand what you should be doing. Okay. At the highest end, and where we'll start, though not where we'll finish, we'll go with our old favorites, response time and throughput. Right? No matter how much computers change, these still remain the dominant goals of most of these systems, certainly any general purpose system or non-real-time system that we're operating on. Right? So if you're looking at something and it's not worried about battery time primarily first because it has no power connection, it's operating on radio waves, you're probably worried about how fast does my code run. Or if you are a data center manager, how many jobs per unit time can I push through this system and monetize, right? Or to get away from things that are quite as mercenary, if you're a GPU, I don't really care about how long it takes to render a pixel. I'm worried about how many millions of pixels per second I can actually be pushing out, right? So throughput is the better way of looking at some of those problems as well, and things get designed accordingly. Okay. So if you think about these, even just as simple goals and the way that things are evolving, right, you can already see, as I mentioned, that the deal has changed. All right, so if we look at response time and throughput, if I replace one core with a faster version, how do my response time and throughput change? Yeah, so response time is definitely going to be lower. Throughput, assuming that you didn't have to do anything hinky to the rest of the design to do so, right, should also go up. In general, making things faster also increases throughput, although this is not universally true. So there's some very simple optimizations like buffering that actually reduce response time, make response time work, but make throughput better. You can play around with some pathological cases. But in general, making things faster also improves throughput. What about adding more cores? What is adding more cores going to do for, yes? Yeah, so if I only had one thread that I was running, that was my workload, and I had more cores, it probably didn't make anything better. And it might even made things worse because my core might not be further away from resources it needs. Or the other question is, well, what did I have to give up to add more cores? Did I, lose half my cache to replace it with cores? These are trade-offs. But in general, if you're looking at least peak throughput, adding more cores should be good. Right. We're going to start as we did before with response time. We will come back to throughput. There are various points in the space where it's going to really sort of be the metric of merit. Even some of the things that we're doing to make response time better for a single sequencer, if you look at it all the way down at the instruction level, it's a throughput optimization. Right? So in fact, a lot of the optimizations we're going to do for program level response time for latency are throughput level optimizations at the level of a single instruction. Right? For the same sort of reason, as I said with the GPU, I don't care about one pixel, I care about millions per second. Same way with the CPU, I don't care about one instruction. My single instruction latency is basically irrelevant. Yes. Yes. So the nomenclature, so the question was, for those following along later at home, do GPUs have the equivalence of cores? Yes, so GPUs, you can look at them as a multi-core processor. The different companies have slightly different names for them. So NVIDIA would call them SMs. I think the right way of looking at each SM is logically like a core. Now that core is itself very heavily multi-threaded, which we'll cover some weeks from now. But between different SMs, you have many of the same issues that you have between multiple cores on a multi-core model. Right, so it wouldn't be, for instance, logical to talk about a less than one SM GPU. A one SM GPU is sort of your minimum unit in the same way that a one core CPU is your minimum unit. Okay, so having throughput and response time numbers is good. Just presenting them is bad, right? If you don't understand them, then you're not doing a very good job of being an architect or microarchitect, right? That just means you ran some numbers. You want to actually understand, what the heck does it actually imply? Okay. So again, we're gonna go back from definitions. For all those of you, who still remember 331, again, this is review now, so you should be familiar. We're going to define performance as 1 over execution time. Great, simple. And we're going to stick with that no matter what sort of design we're looking at. We don't really care whether it's 1,000 threads of GPU or it's 2 wide simple superscalar in order. It doesn't matter. This is just a definitional truth. Yes. So execution time is what you tend to optimize for a particular task. I think is the right way of looking at it, right? So if I have a task and, how long does that task take, right? That's a useful metric of performance because I can turn that into other things depending on the nature of my workload, right? So if I have a sequence of tasks that have to be completed, I want to make each task shorter and then my whole sequence is shorter. If I make one of my tasks shorter, I have now freed up those resources to spend them on something else later. Right? Yeah. So again, definitional. This has not changed since it was sort of formalized in the 80s, but we're just going to make sure everyone is on the same page. Okay. And as I said, decreasing the response time almost always improves throughput. You can come up with pathological cases where it doesn't, but it's a good rule of thumb. The reverse is not true. There are a large number of throughput optimizations which make response time worse, right? It's not a symmetric relationship. Okay, so stop me if you've seen this one before, but we'll go on through it. We're just going to make sure that we're, again, all paging it back in from yesteryear. So if a computer A runs a program in 10 seconds, the computer B runs the same program in 15 seconds, how much faster is A than B? True in the definition. And we're going to say it is a performance ratio of 1.5 or a speed up of 1.5, or A is 50% faster than B. All of these are going to be equivalent statements. Okay. Now, the more complex your system, the more that even measuring time itself can be a little funny, right? So if you are a single user bare metal system running exactly your code in some embedded device, then wall clock time is elapsed time. That's basically the way the world works. For everyone else, your program might not actually be running all the time. The OS might not have scheduled you, right? There are minimum granularity issues in even trying to measure when you interact with the scheduling system, right? So if you want to understand the difference between this fractional millisecond and this other fractional millisecond, measure a larger task, because at that point the interference from any other aspect of the system is too high, right? Timer interrupts going off is going to change your timing at that point. Right? So if you look at things that are down at the microsecond level, they actually become very, very difficult to measure accurately unless you're using something like a hardware performance counter. And even those are only statistically interesting, right? We are not equipped to really tell you exactly how long each instruction in your hello world took, right? You will not get good feedback on that from any measurement system. It's too small a measurement for what everything is designed to measure. All right, if you want to understand the average amount of time that it took to print hello world in a loop of a few thousand times printing hello world, we're good, right? But if you want to understand exactly, how long each load in the print function took, yeah, you're not going to get those stats. Okay, so try to measure the right thing. Again, in a multi-processor setting, anything that you are probably familiar with running on that isn't an embedded system, there are always at least 2 things running. Right? There's at least the operating system and the user program. If you go to the cloud, it gets even more fun. Right? So the cloud, you have the hypervisor, which is managing your operating system as a guest application, but the operating system doesn't actually entirely know anything else about the rest of the machine. It's all been virtualized. Abstract, 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 virtualize, virtualize, virtualize. So understanding why a particular run took a particular amount of time, you won't even be given that information. And to the degree that you could even gather some of that information from someone like Amazon, that's been monetized. Amazon will sell you a service to tell you information about, what your actual resource usage were on the machine if you were operating on a consolidated machine that you didn't own the entirety of. So measurement's hard, even if we're just looking at how long did it take, right? That can be a tricky question. And in particular, if the answer for how long it took is mostly dominated by it sitting there and waiting for someone else to talk to it, I will admit that most of the things in this class are not going to help much, right? I can't give you any deep insights on making the speed of light faster for your optical networking, or otherwise improving the random responses across a globally spanning cloud. But anything that is looking about your processing time or some of these other overhead interactions, you will benefit from the things we look at in this class. Right. Okay. So this is what, if you are an architect, you probably want to spend most of your time optimizing because it's where you actually have leverage. So assuming that you actually get a reasonable measurement of the CPU time, and note when we say CPU, we don't just mean time spent on the just the core components. It's also including all the stuff going on in the memory system. We mean basically the time spent on things that are logically part of your classic 5-component of a processor resources, right? So everything other than external events or scheduling overheads. Okay, anything other than other people using your resources, although again, in multiprocessor systems, some of these resources are shared, and getting appropriate accounting of exactly how much you were using and someone else was using may be functionally impossible, right? So if all 16 of your cores share the L3, how much L3 did you get? Can you measure the counterfactual of what your performance would have been if there hadn't been any other people sharing? These are interesting things in practice in performance debugging and evaluation. Okay. Similarly, all of this is going to actually turn out to be pretty workload dependent, right? If all I want to do is multiply matrices all day, right, then I have very different performance sensitivities to these other interactions that I might be dealing with, as well as the optimizations I'm performing locally if it was just me. Okay. Okay, we're going to assume that you all hopefully remember what clocks are. Now, one interesting thing to note, by the time you get to a modern era processor, unlike your 331 era processor, this is a flat out lie, right? Your clock is not constant. Full stop. So there are a number of different reasons for this. Anyone want to throw a few out? So let's sort of split these into sort of there's a mechanism and a goal, right? So what is one of the reasons from a goal perspective that it has become intensely desirable to not have a constant clock? Yeah, so there is a relationship between how fast transistors can switch and the voltage that you are putting on them, right? So if I'm willing to allow my transistors to be slow, and it's not a linear relationship, I can drop my voltage and I get a quadratic savings in the energy of switching. I get CV squared, right? And in particular, this is even, well, dynamic voltage and frequency scaling has been around for a while. This is even more important in a multiprocessor setting because you might not be using all of your cores all of the time. So why are you flooring the accelerator on a core with nothing running on it? Yes. Yeah. So undervolting is part of the dynamic voltage management regime. Yeah. Now, changing the clock period is very slow relative to the clock period. So if I've got a 5 gigahertz clock, right, you're talking about 200 picoseconds for one clock cycle. I want to change that to a different frequency. You're talking microseconds, tens of microseconds, because clocks have to be very stable. So what you always do first, right, is you actually start reducing actually the way it works in practice. I start slowing down my clock, which is actually a deeply analog process, which we will not talk about at all. But if you're interested in phase lock loops, go take some EE classes. Anyway, so you slow that down and then you drop the voltage. You don't want to do it the other way around. Bad things would happen. Time constants are not your friends there. You want to slow down and then turn the voltage down until it meets the timing that you want it to have. Okay, so big savings because we can put a bunch of our cores to slow mode if they're not expected to be under substantial load because we've got a multi-core. Only one of them might be active at a time. Some of them might even, in fact, be asleep. We can literally actually turn them off, right? So you can do clock gating, right? So if, in fact, if literally nothing is scheduled on this core, I can turn off its clock and it will happily sit there. I leave the power on, but turn the clock off and freeze the state until it's needed again. There are lots and lots of things that are being done, and clock gating is fast. I can gate a processor in a cycle or two, depending. So from a mechanism perspective, we're really sort of looking at understanding critical path timing and sort of engineering margins and these other sorts of things. The other thing you get, in fact, is not just going down to save power. We also get turbo boost, or whatever AMD's equivalent marketing term for it is, which is actually a better way of looking at it is. So you remember that missing component in Dennard scaling where we can't drop the voltage anymore because we're going to go back to cooking eggs? Well, it turns out that thermal processes are fairly slow compared to compute processes. There's a lot of thermal capacitance in a big block of slightly adulterated glass, right? Your special metal sand, right? That is your processor. So that will take milliseconds to tens of milliseconds to actually start to heat up enough that it becomes a design worry, right? So as long as my period of boosting is not too long, I can afford to not be able to pay for my thermals indefinitely, and I can actually run it at or beyond the sort of nominal voltage point, as long as I don't do it for too long and it becomes a thermal problem, right? So your thermal boosting is actually a better representation of what the actual underlying circuits could actually hit, right? So if you look at your max boost frequency in something that you go out and buy today, right, that would have been the clock that they would have been shipping that at, right, if marketing could have let them, 20 years ago, right? That's what the design is actually capable of. That's what the transistors in those circuits can actually run that reliably at, right? You just can't actually afford to leave it at that position indefinitely, or the whole thing will melt itself, right? So, constant rate clock, no. But at any particular point in time, given that it takes, say, 100 microseconds to change your clock frequency, and 100 microseconds is a really, really long time in processor land, we can assume that for local analysis, the clock is constant. Again, an interesting thing as you go to multi-core and larger designs, right? That's constant for one component, right? Your cache does not necessarily have the same clock as your core. Certainly your L3 definitely doesn't have the same clock as your core. It's going to be clocked much, much slower, right? So each component, given some period of time, is going to be stable. If you look at it in the longer view, and there are going to be multiple clocks, so you're going to have to sort of treat them as asynchronous clock domain crossings as you move from cores to caches to off chip. Okay, but we can still do this analysis, and so we can still do the same over to here. Right, same sort of analysis here, except here, the only substitution you really want to make it true is don't look at this as a program. Look at this as sort of piecewise analysis of regions of a program. All right, so here's a chunk of the program that's going to run at a constant clock. Maybe the clock changes. But for each of these periods of time, right, execution time is pretty simple. That region of the program has some number of clock cycles over clock rate. It's just time. Time is time. Okay. And so if you're looking at this again from a design perspective, you can still think about optimizing for any of these stable points, right? There's still circuit and ISA and technique trade-offs in CPI. So all the things that you learned about optimizing execution time in the 331 scales still apply. There's just another layer on top of them as you think about how it's actually going to run across the entire program. So if you're interested in sort of how you can meta optimize these sorts of things, there's some good papers that came out about 10 years ago in thermal boosting. Okay. So let's keep going. Again, the equations are going to look the same as they did in 331, but now you're going to understand them slightly differently, right? So that's all that's changing. So 2 gigahertz clock for 10 seconds. And if we want to have computer B run this program in 6 seconds, but uses 1.2 times as many clock cycles, you do the math, you do the unit cancellation, right? You'll get back to the same sorts of things. These are literally the same slides that were in 331. I know none of you should be remembering some of these like first or second week slides from 331. These are the same slides, same example. Okay, so that's why I'm going through them fairly fast. Please also stop me if at any point, for those of you, particularly MS PhD students who weren't in 331. Yes. Mm-hmm. Mm-hmm. Yes. So if you look at the spec sheets, right? So you'll have something with like a nominal clock of say 3 gigahertz and a boost to 4 point something. Yeah, I mean there is a dynamic range that the circuits and voltages make sense for. And again, in any point in time, the clock is actually very, very stable, right? So let's say you're running currently at 5 gigahertz, right? And for the next 100 microseconds, you are running at 5 gigahertz. That needs to be 5 gigahertz plus or minus a couple of picoseconds, right? And 200 plus or minus a couple of picoseconds. You cannot vary much. Otherwise, your circuits really won't work. They're pretty thin engineering margins, right? So from the analysis perspective, yes, over 10 seconds, your clock may vary. So is it reasonable in a modern processor to assume that the clock is 2 gigahertz for the whole of 10 seconds? No, but if I just said 10 microseconds, right, everything else here would be, the math would be basically the same, and it would definitely be true. And your program might, your processor might run at 2 gigahertz the whole time. Right? There's no reason that it necessarily up or down volts. This is just another knob that can be optimized dynamically during execution by your power management unit. Right. So again, the right way to look at it is all the equations we learned before aren't wrong. They're just local. Right. They're making assumptions about what stays constant that are no longer necessarily constant globally, but in any small window, nothing has changed. No. Okay. Flip back to, okay, clock cycles per instruction, right? So this is going to get more and more true the more complex your design it becomes. So CPI is not only a sort of key metric to be measuring, but it's a good way of thinking about things. Now, one of the goals in this class is to get us beyond the Flynn limit, right? Which we'll breach fairly quickly. So the Flynn limit is CPI 1, right? So if you think back to what was the best number of cycles per instruction you could have in your design that fetched 1 cycle per instruction, well, clearly the best you could have would be CPI of 1, right? Your pipeline design, your single cycle processor is by definition a CPI of 1 if you ignore the memory system. Your pipeline processor, when there are no pipeline stalls, also hits a CPI of 1, and that's best case. But we're going to go to CPIs of less than 1, right? By throwing some parallelism at the problem. Right? We're going to go superscalar. So we're going to start measuring things in IPC. The only key difference between instructions per cycle versus cycles per instruction is that CPI is nicely additive and IPC, well, that's how fractions work. You just can't add them together. But all of the systems that you are familiar with all had goals of IPC greater than 1, which is equivalent to a CPI of less than 1. They would have been considered radically unsuccessful if they were still sitting on the wrong side of the Flynn limit. But we'll get there. Now, what's going to happen is, as these systems have grown and expanded, as we move from our sort of late 1980s view of the world to our, all the way up to our mid or late 2000s, sorry, view of the world, the ratio of how different these instructions are going to be is going to change as well, right? So if I had a relatively slow 1 megahertz processor, and I got one level of cache, and then everything after that is an off-chip memory access, but memory isn't that radically slow. Maybe it's an extra 50 cycles. Well, now again, think, okay, I got my 5 gigahertz processor. So 200 picoseconds for an add. Or if I go all the way to main memory, which is going to take me, let's just round up, let's say 100 nanoseconds. You can get faster than that. Oh, let's be nice. Let's say it's 50. So in 50 nanoseconds, how many for a load that went all the way to memory? What's the ratio between one load versus one add at 200 picoseconds? I know it's too early in the morning for arithmetic. It's let me put it on the board again. Just to get a sense of why we have the concerns that we do. So if we had, old system A, let's say late 80s, and let's say we have a 1 megahertz clock, which means we have a 1 microsecond clock cycle, last I checked, right? And then memory, main memory DRAM, let's say it was probably actually, still not radically. Let's say it's 100 nanoseconds. Let's see if it's even longer. That's right. That's actually the actual internal access. Let's even say that it's a full microsecond to access my my DRAM at the time. And then you go to recent. And now you're at 100 picoseconds for your 5 gigahertz. And we're at, say, 50 nanoseconds for our memory access, right? So here we were going from, a 2-to-1. It took me like an extra cycle to go out. In fact, if you look at there's a good investigation from the this is a little earlier than this, from the DEC Corporation, investigating why their performance wasn't what they thought it was, and they were going down and breaking down all these, sort of an early investigation of, well, let's actually go measure the CPIs rather than just think real hard about them. In around 1980, 81, sort of the dawn of actually quantitative based rather than almost arguably Aristotelian approaches to architecture design. And you're looking at things where, it took you 10 cycles to do an add, and it only took you like, 12 cycles to do a load. So what was the big deal, right? By the mid 80s, you're like, 2-to-1 to, 1-to-10, trying to get a little expensive. Here, right? This is not just expensive. This is catastrophic, right? So ratio between these two, I check, that should be what, 250? 250 to 1? And that's not a terrible ratio in the grand scheme of things, right? So when we say that not all instructions take the same amount of time, we really mean there are some huge gulfs between the different classes of instruction, right? So we do need to actually pay some attention to that. And yes, we have a bunch of techniques to mitigate that, right? Hopefully not every instruction is going all the way to main memory. If it is, you should look into your workload and understand whether or not you're using the right algorithms or the right machine. But okay. Now, we do care about the average case. Right? So again, as I said earlier, we don't really worry too much about the latency of a single instruction, but we do worry about the latency of instruction classes, because those can be indicative, right? So there's not actually a whole lot of variance between different adds, right? The only variance you're going to have between different adds is, basically the operand readiness, right? But variance between loads is going to be as does it hit in the cache, so you'll get a distribution. But that average is meaningful. That average actually tells you useful things about the system. Okay, so we're looking at the average clock cycle per instruction. You can look at it overall. So lower is better. You can look at it per individual class, right? And if you have the same ISA, this gives you a lot of insight into how things are working. If you have different ISAs, it's pretty complicated. You can imagine the degenerate case. I have an ISA where my entire program is one instruction. So my cycles per instruction might be some stupidly large number, but it might still be faster. Right? It's not a good way to compare across the two. Again, we'll get to the execution time equation where you have all three factors that you can do cross ISA comparisons. Just a second. And that's sort of one way that you can even think about ASICs, right? Imagine them as if they were a single instruction that was just a million cycles. It's one mental model for doing application specific integrated circuits in the middle of your program execution. Okay, so here we go. Back to our good old friend, the execution time equation. All right, CP time is instruction count times CPI times clock cycle. And the reason, again, that it's broken down that way is this finally lets you do ISA agnostic population of your performance comparisons. All right, so your different ISAs are going to manifest as variance in the number of instructions, the variance in the CPI, and the influence that they have on the clock cycle. Right, but if you multiply all those together, you will get time. Right, so instructions times cycles per instruction gives you cycles times the amount of time that it takes per cycle gives you time. If your unit cancellation doesn't cancel, well, one of your terms is upside down. That's a common mistake on simple exam questions. Okay, so whether it's 1980 or 2020 doesn't matter. These are still the three key things that are going to affect the execution of a particular program. Now, it's still a lot easier to think about this in the uniprocessor model. How you want to sort of play this out on the multiprocessor model is a little more complicated. Right? So for instance, in the multiprocessor model, you need to sort of look at perhaps a notion of the number of instructions on the critical path through the program. Right? If you have some thread that's sitting there idling and spinning and executing a bunch of instructions, waiting for the other threads to finish, this is perhaps not an easy model to map. But since we're still living in single processor land for at least the first 2/3 of the class, we don't have to worry about that nuance yet. Right? Okay. So to put it all together, here's how you'd use it. I have computer A and B, same ISA, clock cycle of 250 picoseconds for A, average CPI of 2 for some program. Computer B is the clock cycle of 500 picoseconds, average CPI 1.2 for the same program. You can answer which computer is faster and by how much. If we told you about two different programs, you would not be able to compare them, right? If I run Photoshop on one machine and then I run, Call of Duty on another, I can't tell you which is faster. That's not how you compare things, right? So if they were different ISAs, but I still populated all these for the same program, I could actually still compare them though. Right? I get a different number of instructions to get it. Yes. So if they're not the same program always have the same I, right? No, if it's on different ISAs, I would be different. Oh, okay. Right. So I have an ARM machine, I have an x86 machine, I run Photoshop on both of them. Right. My nominal task is the same, but the particular actual program binary would be different. Number of instructions would be different. My CPIs would be different. Yeah. So from benchmarking perspective, I need a benchmark, but I have an implementation of that benchmark that can be run on each of these systems, and it will play out differently. So hopefully we can all do multiplication and some basic dot products, and about as difficult as most of the math gets, right? And again, we look at distributions for average CPI for each of the dynamic mixed frequency of instructions. So again, as I said, hopefully we can do dot products, and you can get overall effective CPI from a program by looking at its non-aggregate breakdowns of operation mix, right? So if I know that 50% of my ops are ALUs, they take one cycle per instruction. Average CPI again here, right? This is going to be some distribution. Some of your loads are going to take one, they hit in the cache, great. Or they hit in the load store queue, which we'll hit later, even better, right? And some of them will take, well, 250. So you're hoping to get that average access time down. Again, we don't worry about one instruction. Worst case, this does come up. Have any ever heard of WCET? No? Okay. So if you're looking at sort of, say, embedded real-time systems, mission critical stuff, they worry about worst case execution time. So they don't care about your average. So they just basically assume that if you can't guarantee me what the distribution is at any particular point in time, I have to use 250 as this value, not 5. Obviously, that would give you a very, very different answer here if 20% of them could take 250. Right. So, but we're worried about average case because we're worried about general purpose processors, a thing that totally still exists. Okay. This does, however, also tell you, right? And again, why we want to look at these non-aggregate data is it tells you where you should focus your time, right? So once I multiply these out, I get the relative impact, right, on my CPI. So if I have a finite number of engineering hours to throw at a problem, I'd probably want to put them here and not here, right? My loads are going to give me a lot more bang for my buck than optimizing my stores. Okay, we can look at different scenarios pretty simply. All right, so how much faster would the machine be if we had a better cache and reduced the average time to 2 instead of 5? Again, fairly big swing. If we just had better branch prediction, right, not much of an impact. There wasn't that much to start with. 2 ALU instructions at once, which we will cover in not too many weeks. Very doable, right? Fairly modest. Now, the trick in also understanding these, this is telling you what you could potentially get from it. One of the things that you will hopefully learn in this class versus your previous ones is how realistic is it to expect that you would be able to accomplish these goals. How much would you have to invest to do them, right? So it's going to turn out that some of these things are going to be a lot easier than others, right? So getting 2 ALU instructions to be executed at once is actually very achievable and pretty cheap. Dropping my average memory access time from 5 to 2, I make no guarantees you're going to be able to do that. It would have a very big impact if you could, but this could actually be, depending on the workload, again, either trivial or impossible, right? Whereas this at a design level is actually quite easy. So hopefully, over the course of this class, we'll get a good sense of basically what is expensive and what is cheap, what is easy and what is hard. Okay, so let's just sort of review. These are the 3 components. Learn them, love them, burn them into your brain, right? But there are a bunch of different things that are involved in computing the CPU execution time. So let me give you the classic example. Let's say that my workload of interest is sorting. It's a real workload, for databases, big scale networking sort of things. People actually still worry about that. But let's say that my workload of interest is sorting. If I pick a particularly terrible sorting algorithm, say permutation sort, where I permute my data set and check if it's sorted, good old factorial running time, right? Nothing I do in hardware is going to fix that problem, right? So some of these things are not under the control of the hardware designer. So let's think about who all the players are and what role they're going to play. Right. So if you were a programmer, which of these three? Again, we're not doing clickers this year, so clickers would come in. By next week, we'll be doing Cahoots, but for right now, we can just do a show of well, I'd say a show of support, but I imagine at this hour of the morning, it's going to be a meh level of enthusiasm for any of these options. So we'll see how much meh we can rally, right? Hopefully it'll take less than 15 votes. Yes, that was a topical joke. It wasn't very funny. It's fine. Okay, so which of these options can a programmer influence? Can a programmer influence the instruction count? Support. How many people are supported that? Yeah. As we just went over, if you have a particularly terrible algorithm, this can take arbitrarily long. Okay. Can a programmer influence the CPI? Weakly, they can. I'm going to argue that they can, but not directly. Right? Can a programmer influence all three of the factors? Yeah, no. The cycle time is not really something that they can do. So that burns out both of these. Certainly, it's not none of the above. I'd say the closest answer here is actually B. All right. What about a compiler? Or for those of you who are intent to run nothing but Python for the rest of your life, the interpreter. Question or? Mm-hmm.
So exactly how does the
We'll get to that in a couple of slides. Yeah, I'll go over that when we have the full table. Okay, how about the compiler? How about the translation between the expression of the program and its actual executable form? Right? What influence can that have? Does that influence the instruction count? So it's creating the program binary and only one person is saying it influences the instruction count. Okay. How about the instruction count and the CPI? Can your compiler change your average number of cycles per instruction? I'm going to nod yes, and we're going to just pretend you all raised your hands. Okay. Can the compiler influence anything we're doing with the cycle time? No. Right. At least not in any of the designs that we are interested in discussing. Okay, and finally, how about the instruction set architecture itself? Does the instruction set architecture influence the number of instructions that it took to do your program? Yes, right? If I give you the factor polynomial instruction, which was a real instruction in the VAX ISA, it will take you fewer instructions to factor polynomials. Right? Does it influence the instruction count and the CPI? Well, yeah. And the choice of instructions you do influences how many cycles on average it takes to do those instructions. Right? How about the cycle time? Does your ISA have an impact on cycle time? Yes, because mostly of the former, right? So if I ask you to do incredibly complex things, right, your design complexity will be either easier or harder to make lean and fast, right? And finally, the poor people who are involved in actually implementing all these things that we ask them to do, they don't get to control these upper pieces here too much, right? These are logical cycles. But they do get to influence the cycle time. If your circuit designers are better, your cycle time will go down. If your circuit designers are terrible, right, even if you have the number of cycles that logically things should take at the architecture level and the microarchitecture level, right, you say, I got 5 stages in my pipeline. And then the guy who's designing it, doesn't actually know how to build a latch. It's going to be slow. Okay, so to put these all together, you can see that some of these are dimmer than others. Okay, so at the algorithm level, right, obviously the instruction count is deeply influenced by what how many operations you're attempting to perform. The efficiency of the algorithm really comes into play here. But there's well, you cannot directly control the CPI. You can have a big influence on it. Right. So let me give you a concrete example. many years ago, back when I was a grad student, there was a fellow grad student who was looking into some string matching algorithms of the day. And the state-of-the-art algorithm, there was a linear time algorithm. There was an older algorithm, was an n log n algorithm. But the n log n algorithm was faster in practice because the linear algorithm was linear in the speed of disk, because nothing fit in memory and the whole thing just was swapping. And the n log n algorithm was cache and memory friendly. So the average memory access time was much lower. Similarly, if you look at decisions to store versus recompute something being done at the algorithmic level, right? These can have influences on locality and other optimizations within your processor, right? So either some things are easily exploited because they're common patterns that we have the hardware to exploit. Other things are maybe fewer instructions or different trade-offs here, but the hardware doesn't handle them very well. Right. So if you are doing lots of memory accesses versus lots of adds, that's a choice that you can influence here, even at the algorithmic level, and they have impacts on your CPI. Right. So how you choose to express the work that you need to be done, right, can have some impact here. Programming language, similar aspects here. Right. So some programming languages have overheads that map poorly, because they're doing management tasks that have poor locality. They're jumping back and forth between the runtime and the sort of user code management. Other things are just very bare or allow you to express things in a way the hardware can optimize. Right. So if you are writing a program in C and you're talking about an array of bytes, you know pretty much exactly how that is laid out in memory. You can understand how it's going to interact with your cache system. If in Python you say, so list of numbers, yeah, good luck with that. All right, understanding exactly how that's going to play out. Now, the scale here can be different, right? The worst algorithm you can imagine could be orders and orders of magnitude worse, right? The worst programming language, well, let's not come up with the worst programming language. Anyone have a favorite worst programming language? I'm going to shout out for Intercal. Go look that one up if you've ever heard of it. It was a joke language intended to make programming hard. So anyway, but this is usually 2 to 4x, broadly speaking. So you can. This is depending on what you needed. This is not as earth-shattering. Similarly, compiler has a very deep influence on both the instruction count because it's writing out the program. So it actually determines finally what the final instruction count of a given program is given the ISA, and the optimizations you do in the compiler, right, are going to deeply influence the CPI. Right? Did your compiler do loop unrolling or not? Changes your CPI. Did your compiler do loop interchange? Did your compiler do dead code elimination, et cetera, et cetera, et cetera, et cetera? Right? ISA cuts across all of these. And then the microarchitecture here, right, doesn't influence your instruction count, but it influences how each of these instructions are implemented. Right? So I could take the same ISA, build a single cycle processor. I mean, my CPI is 1, my clock cycle is garbage, but that's fine, it's a valid design point. Or I could, have a 50-stage deep pipeline. My CPI is going to be pretty high, but so my clock cycle has been really short. Then finally, the actual technology node that you implemented on. So again, think back to that graph from Tuesday, where you took the 386 and just implemented a bunch of different technology nodes. It still scaled, but the only thing that was basically scaling in was clock cycle, right? Nothing else was changing. Okay, does that answer the earlier question about how CPI is affected by these sort of upper pieces here? Any other further questions on that? Okay. Okay, so if you are primarily interested in microprocessors for mostly general purpose workloads, then from '89 through now, the System Performance Evaluation Cooperative has been producing benchmarks on your behalf. And for the low cost of a few $1,000s, you too could be a licensee of these spec benchmarks. They have an increasing number of different subsets. So the CPU benchmarks are integer and floating point. Right? So basically working on primarily discrete or primarily continuous problems. Those are very different looking workloads in practice. They get longer and longer and longer. So, spec 2017, these are trillions of instructions for every one of these benchmarks. Running them on real hardware, not too bad. Running them in simulation at like 100 kilo instructions per second simulated, for trillions of instructions. Well, then you go into an entire subfield of simulation methodology of how to not do the whole thing. Yes. Yeah, so there are a couple different things. So one thing is that real world workloads don't tend to be benchmarks, and that not everyone tends to have access to both the code and the data in order to cross compare them. These also allow you to test for particular things that are of interest to you. So the spec benchmarks intentionally have very little operating system involvement. They are not intended to tell you about how a real system stack is going to work. They're there to measure your CPU. So they want to basically do a pre-stage where everything is loaded from disk into memory. They don't do any interesting amount of I/O if they can avoid it. They don't want to deal with the operating system scheduling. They're like, I just want to compare core to core, chip to chip, how this thing is working out. And yes, there are parallel versions of these as well. And if you wanted to measure other things, if you're doing, say, database processing, there are benchmarks just for that, right? If I want to do transaction processing, which is I/O intensive, which is throughput oriented, I'm going to run a different benchmark, right? So I think the right way of looking at it is, if you don't care about the raw core performance, these are the wrong benchmarks and will tell you very little about what your real world deployment is going to look like. But if you're an architect, you kind of have to care about the core performance a bit. It's certainly a component in all of these other pieces. So this still gives you good insights into pieces of it. Now, the other thing to take into account here, if you go and look up who the companies, this is a consortium, right? Who the companies in spec are, that also tells you a lot about what they're interested in and also willing to allow to be measured, right? So this is Microsoft and Intel and AMD, and right, there are a bunch of players who have particular ideas about what they want to have as marketing compatible data to put out. So these are far from perfect, but they're consistent, right? So you can at least measure them against each other. It's a reasonable yardstick in that regard. There are things for power. There are things for enterprise systems. Spec puts out lots and lots of, there are things for mail workloads. If you want to measure a mail server, there's a workload for that, right? So whatever you think about it, someone probably has a benchmark for it. Right? And this actually comes up when you get new types of systems. This is where it actually kind of becomes pretty interesting. So if you're going out and you want to measure, the various performance and efficiency properties of a smartphone today, that's pretty easy. People have developed a bunch of benchmark suites for smartphones, and they tell you something useful. If you're trying to do this in 2010, it's actually pretty tricky, right? It's like, well, it's kind of like a personal computer, except it's also a mobile device. So we could either take our old, ultra embedded benchmarks on it, which don't really tell us a full story, or we could run our spec workloads on it, which look nothing like what your actual phone is looking like. So these things do take some time to develop. So even though they are grossly imperfect, I wouldn't underestimate and a consensus on what was the right benchmarks among a bunch of companies with some vested interests in having their things look good. There's still a lot of work that went into actually making these meaningful. And there are some, less visible, but still important publication venues whose sole goal is to characterize workloads and understand whether or not these are even, what is the benchmark suite measuring? What is the inter program or even within a program as a function of time diversity of features, right? So you can actually understand the art of benchmarking even has its own sort of subdiscipline. We will not go deeply into this in this class, but benchmarks are not necessarily programs. But broadly speaking, the other way to look at it is, as I said at the beginning, one of the real challenges with real world is there's a lot of proprietary stuff that goes in there, right? So if you want to understand how things work in a Google data center, unless you are Google or are working for or with Google, you will not have access to the data that will allow you to answer that question, right? And there's a lot of work on synthetic benchmarking. So can I derive a good representation, right? That's a tricky business in itself. Okay, so what do they actually put out? Everything is done relative to a common reference point. That's again also how you get these nice, number go up charts. They all take the same initial baseline, and they just show you how these things have improved as a function of time. So you can, the other nice thing about some of these benchmarks is you can run them on very old hardware, right? So you can actually have a consistent point in time that is your baseline, and so the numbers go up year to year. You can also sort of see here that the spec ratio against this one common baseline process. These are basically the ratios relative to the same baseline vary a bit. So some things are 6 times faster, some things are 22 times faster, right? Your mileage may vary quite a bit, right? And I won't go into the particular details of these, but these benchmarks span from chess playing to media encoding to graph search, right? To running a compiler, right? And this also shows you some of the difficulty in cross-comparing different designs, right? So certain things are outliers, right? And the same has been true. This is back in these are 2006. I think the 2006 numbers on like 2008 era machines. But if you go and look at the spec 2017 numbers, you get the same effects, right? So all these values have a lot of variance. So from no single measurement of a machine should you with high confidence predict how it's going to do on some other yet to be determined workload, right? Yes. So these are run independently some number of times to get a good average, and then your spec ratio is defined. If you submit these results, you actually have to submit your entire software stack, how they were compiled, et cetera, et cetera, et cetera. So you are issued the source code, and then you're free to compile it and otherwise optimize it as you see fit on your particular machine. So. Then you get this number down here finally, geomean across all these, right? And you'd say, oh, it's 25x faster than the baseline, even though sometimes it's 190x and sometimes it's 19. So use the geomean to help smooth out these outliers and get the marketing departments to say something reasonable. So when we try to compare everything with a single number like that, it's what I really wanted to show those to you is just that it hides a lot of information, right? So again, if all I told you was this 25.7, how are you going to guess the rest of these? Right. So you really have to understand what is it that you are interested in measuring. What are the cases of interest to you in your workloads? What are the properties, again, from the algorithm on down, and how do they interact with choices you make? So MCF, multi-commodity flow, is a flow algorithm on a reasonably large, few hundred megabyte graph, right? So that actually tells you some things about what you should expect in terms of its behaviors, right? It is going to be a pointer-based algorithm. I'm going to be moving from memory location to memory location. I'm not going to have deep locality. It is going to interact in a complicated fashion with my caches. Hundreds of megabytes is larger than my caches. There is going to be some memory behavior, right? Whereas if you look at something like, bzip, where, I'm going to take some chunk of data, I am going to operate on it to recode it locally in little tiny chunks. They're actually fairly cache friendly. I should expect very different behavior, right? These are in line with expectations, right? Bzip should perform a lot better than an MCF, but the relative performance benefits may also be low as a function of, say, increasing my memory size versus that baseline processor, right? Because everything might be pretty good at bzip because the algorithm is actually very hardware friendly, right? So understanding the properties of the algorithm, understanding what your compiler may or may not have tried to do right, will help you interpret these sorts of results for your workloads, right? You should ultimately get an intuitive level sense of whether or not certain things that you're want to do at the program level are easy or hard to accelerate with hardware, right? So again, reproducibility, spec ratio, I'm not going to dwell on this slide. So power was not something that was early on in benchmarking, took a while to come out, is increasingly important, right? So there are benchmarks for that are very focused on power and energy. So if you're looking at, in particular, the emerging IoT scenario where many of these things are form factor or battery or otherwise limited, coming up with these sorts of metrics is going to be pretty important. Looking at new benchmarks for the IoT is also going to be important. The one thing we want to look here, this is still in sort of the server space. The interesting thing for the spec power benchmarks is that they have a notion of nominal load on that machine. And here you're going to see a bit of a problem. It's gotten a bit better since late 2000s, early 2010s, but there is still a fundamental disproportionality here. So you note that at 0% load, this machine was pulling down 141 watts. So with nothing running on it, it was 141. With fully loaded, it was 295. Right. While the specifics have gotten better, the problem fundamentally remains. Right. Turning your machine on at all has a non-zero amount of cost. Right. So this is one of the key reasons that data centers try to consolidate, manage load, turn machines on, off, and dump multiple things on one machine if they can. From an energy efficiency perspective, there's still a lot of work to do here in what we would call power proportional computing. Right. Goal really since the terms were coined in around 2007. Right. So similar here for Intel Xeon of the same era. Right, same sort of problem. Right. So this is just sort of going deeper. Again, if you're looking at what load data centers actually run at, the average is usually close to 30. It has to do with burstiness in workloads and responsiveness and how SLAs work. If I keep my machines too overloaded, well, then I can't actually meet my peak demands, which can rapidly rise because it can take minutes to bring a bunch more machines online. So I do actually have some trade-offs there as a data center operator in not operating at my maximally efficient power point. Right. So from an efficiency perspective, I want the machine fully loaded. From a responsiveness perspective, I want the machine weakly loaded. Right. So trade-offs abound. Right. So again, the community has been working on this for 15 years. We've gotten better, but it's still a fundamental problem. Okay. Page back in Amdahl's law. It will come up repeatedly. Now I will also give you sort of a forward pointer. So in a 331 context, you look at Amdahl's law pretty directly, right? I have a portion of my design. I improve it by some factor. Some of it is not affected. This gives me some bounds on how much better it could have gotten. By the end of this class, you'll have seen a couple of other variants. The Amdahl was an optimist and Amdahl was a pessimist variant of this, right? So this is a sort of universal truth, but the nuance comes here. So this formula doesn't change. This formula is right, but the affected portion can often be global and non-uniform, right? So implementing this improvement factor can have global effects on the entire design, right? So let me give you an example. I parallelized my program. Okay, great. I now have several cores, so my overall time to run the thing should go down by the portion I parallelized. But now that's where the nuance comes in. What did I have to do to my code to make it parallel? It's not the same program anymore, right? I didn't just suddenly say, let there be cores, and now my program is parallel. It's not how it works. I had to rewrite the program, which means there might be basically no unaffected portion of my program. Maybe my synchronization costs had to be added. I had to change my algorithm to be parallel friendly, right? Maybe the synchronization costs grow as a function of the number of cores that you were adding. I can have both a positive and a negative aspect here. Or maybe by parallelizing, and we're just about out of time, maybe I have changed the working set of each of these threads and suddenly everything fits in cache. Right? So you'll see both the Amdahl was an optimist and Amdahl was a pessimist version of this as we proceed later in the course. But for today, let me just jump to the last slide here. So again, recitation this week, we'll be reviewing responses to self-assessment quiz, so do take it. And next week is more review. So I'll get those slides up. Hopefully the next couple of weeks slides will go up this weekend. Okay, see you all.